Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
Robert, another
Yes.
week has gone by.
Another one.
We are here again. Robert,
The year seems to be going faster and faster and faster, and it's just kind of running me over, folks. So ignore me.
you want to share with everybody what happened last night? What did we do?
Oh, what did we do? Well, I gave a talk on planetary interiors and a little bit about how we know what we know about planet interiors. And we also went out and before the talk and looked at the comet in the sky that's up there right now. And it's getting up to where it's pretty high in the evening sky. So it's an easy target. I spotted it with eye before we spotted it with binoculars and everything.
Yeah, it's actually a fantastic sight. This is
It
the
is.
first real good comet probably since the late 90s with Hale-Bopp and
Hale-Bopp.
Hyakutake.
Mm-hmm.
And so it's been a while, nearly, 2.5 decades?
Right.
Essentially. So we've been-
25 years?
I remember people writing about it just like a year ago. There's been a drought of really bright comets recently. So it's just, a random sort of thing that happens, of course. But this one here is actually a really good one.
It's a really good one. Yeah.
You want to show a picture maybe of it?
Okay, we
in
can do that.
In case people haven't seen it before.
So,
So a few days ago, the comet swung around the sun as viewed from our position. So it's now in the evening sky.
right.
So as soon as the sun sets, then you get out, look towards the west, and you can't miss it, especially in a dark location. Wait till the sun has set enough, but not too much, so that it's getting dark,
Right.
and you should easily be able to see the comet. And when it's still bright, one of the things you can do after the sun has set is if you find yourself a pair of binoculars and scan in the western sky.
Right. And I was going to comment that, you should probably do this soon. As you can tell from this chart on the left, by the end of the month, it's up high in the sky. It's moving fast. And it's also going to start dimming. And as I said last night, you could spot it with your eye. It looked like it's just smudge across the sky.
Yeah, and
So-
its tail was pointed, I guess you would say, when you're staring at it, it would be to the upper left.
Mm-hmm.
That's sort of the direction of the tail itself.
It's always pointed away. Well, one tail is always pointed away from the sun.
Yeah.
The other tail is kind of swept because it follows in the orbit.
Yeah, do you remember what the primary substance of those two tails are?
The one that points away from the sun is ionized material.
Yeah, a gas.
A gas. And the other tail is dust.
Yeah, exactly right.
It's particulates.
And the first view that I got of the comet, because you could see it for a while in early morning, so you had to catch it just before the sun rose and try to catch it. And people did, it depends. I think down in the southern hemisphere, people had a better view of it in the early morning than we did here in the northern hemisphere. So I didn't have any luck really seeing it then. And you had to be careful because, of course, you don't want to wait long enough that the sun peaks over the horizon and you have the sunlight going in your binoculars
my
or
eye.
telescope.
Yeah.
That'll be the last thing you see,
All right.
So you got to watch out for that. So when it went by the sun a few days ago on Sunday evening, I finally was able to spot it. And the weather has to be clear in the west. We had a lot of clouds, a
Right.
couple days before that. And so the image of the comet that you see there on the right is actually just holding up my cell phone and just pointing it into the eyepiece of my telescope and snapping an image of it.
And extra bull ask a question, two tails. I want to mention something. There's, like I said, one
These
is
are
an
two
ion.
stories, right?
Yeah, tale of two tails. One is an ion tail. That one you will not be able to see unless it gets really bright with the naked eye. You've got to have long exposure photography for it to show up. The particle tail, however, the particulate tail, you can see with the naked eye. In fact, that's what makes it the smudge across the sky.
Yeah, the sweeping sort of display that you see on a typical comet
Right.
is the dust filling out that space.
That's
In
it.
fact, it's the dust that re-enters it comes into the Earth's atmosphere as meteor showers.
I was about to say, we may get a new meteor shower out of this comet.
Yeah, so if the orbital alignment is correct, if the Earth passes through that material, then we will. In fact, that happened with the Comet Swift-Tuttle a few years back.
Right.
This would have been, I think, the late 90s, where the comet had passed through and repopulated the orbit that the Earth intercepts of that comet.
And we had a real nice shower.
Real nice one. A lot of what we call fireballs. So, larger than average size that we normally get in the Perseids in the August of every summer.
And I guess that bears mentioning too. The meteors that you see in the night sky, usually the particles that are hitting the Earth's atmosphere are about the size of grains of sand. So when you see a fireball, you're still not seeing, a Volkswagen or something like that hitting Earth's atmosphere. You're seeing maybe a baseball size piece.
And the other thing to catch is that during a meteor shower itself, the meteors that are associated with the shower all seem to be coming from a single location on the sky. Right. And there are random meteors, of course, that come from different directions. And those ones you can easily tell because they come in a direction that's completely different from the one that's coming in, like from the Perseid meteor shower. Right. In fact, the name Perseids is the location, the constellation in which these meteors seem to be radiating from.
Is the Perseus.
Is where
and in fact, that's what they call it, a radiant, because they all seem to be coming from that one location.
Yeah. And the other thing is the Perseid meteor shower has been going on for thousands of years. Mm-hmm. And people have recorded this information so we can look back in the records that survived till today, be able to see that people recognized the meteor shower back then. But these meteor showers don't last forever. Eventually, all that material gets used up. Yeah, exactly. It gets vacuumed up by the Earth, and it gets dispersed, and eventually it dies out. And so there have been other meteor showers in the past where they're not so prominent today. You barely recognize that it's a meteor shower. An enhancement over random meteors. Yeah. That's what you'd be looking for. But yeah, so the image on the right is just taken through 12-inch Dobsonian telescope, just hold and shoot, as they would say nowadays, I guess.
I could have put the one that I got holding up my camera, but you had to zoom in to be able to see it. It's a faint smudge.
Yeah. So it's only going to get better. So hopefully everyone has good weather.
And we'll be able to see this.
And we'll be able to appreciate it. The tail is really long. Mm-hmm. You look at it with your eye, it's many degrees across. So it's going to be a good sight. And we'll see what happens. But as it gets into darker and darker skies, it's just going to get that much better.
Right. Definitely go out and try to see it, because these don't happen very often.
Yeah, and you never know when the next one. You might be waiting 50 years, or you might be waiting 5 years. Who knows?
Yep. And there's the name of the comet. So Tsuchinshan-ATLAS.
So the comet itself, when it went by the sun, made closest approach as viewed from the Earth, you can see an image captured in the general vicinity of the sun by the SOHO spacecraft. So this spacecraft is always watching the sun. In fact, the actual visible surface of the sun, which we call the photosphere, is actually blocked. It's represented by the little ring that you see in the middle of this image. Mm-hmm. So it's a coronagraph. That is, there's an occulting disk that's put in front of the sun so that the light of the sun doesn't swamp the view of things that we want to see on the edge of the sun, like coronal mass ejections, particles that get outburst like the sun burps and hurls out this material outwards in space, and we can watch that from a safe distance to keep track of solar storms and these type of events.
We want to see them coming so we can shut down satellites. So.
Well, yeah, that's one of the, I think we talked at length before in the past about things like this, because you're talking about charged particles. Right. And if you have an influx of charged particles around your electronic gear, it's not a good idea.
No, it produces a current in your circuits that's not supposed to be there.
Yes.
So, what Extra Bullet does also ask, is this the comet that comes around every 80,000 years?
Yeah, this is the comet. So there's another reason to get out and look at this comet, because you'd have to wait another 79,999 years for it to swing back.
And I don't think the rest of you have that long.
I wish we did, but I don't know. My bones would be a little achy by then.
I plan on being here.
I wonder if arthritis will set in by then. If you,
it might. It's already trying. So,
but if you think of the orbital period, that gives you some indication of where this comet comes from, and that's way out in the Oort cloud.
Right.
And that was one of the things we talked about last time about Voyager spacecraft, how they're on the order of well over 100 astronomical units away from our sun. An astronomical unit, to remind you, is just the average distance from the Earth to the sun.
Right.
And the Voyager crafts are not even close to the Oort cloud. I mean, they got to go way out there at tens of AU. And that's going to take a long time for them to get out there.
Well, I was just going to point out that, Pluto takes 243 years, if I'm not mistaken.
48.
248, okay.
Yeah.
To make one orbit. This thing takes 80,000 years. So it goes much further out there than even Pluto's orbit.
Yeah, I don't know the lengths of its semi-major axis, but you could easily calculate that from Kepler's law.
You can.
The period squared is proportional to the semi-major axis cubed. So just take the 2/3 power of 80,000 and you got the semi-major axis.
Right. Yeah, I don't think I'll do that in my head. Thank you very much.
It's a large number.
It's a large number.
It's safe to say. But yeah, so even at the speed of Voyagers, I don't know, how fast do they go? I can't remember the speed. You can look it up. It's like 30-some miles a second or something like that.
Something like that, yeah.
Some high rate of speed. It's going to take hundreds of years to get out there.
Right.
Hundreds and hundreds and hundreds of years. So really, we think of Voyager, you make this grand statement, they have left the solar system. Well, it depends how you count it.
How do you describe the solar system?
If you count the solar system as including the Oort cloud, they're not even close of leaving our solar system.
Right. It gets into those definition things. If you're defining the solar wind, the heliopause, they're out of the solar system. They're out of the magnetic field of the sun. If you're talking the gravitational influence of the sun, they got a ways to go.
Well, in some sense, it goes to infinity, right? The gravitational.
It does,
but it gets weaker until eventually you're essentially in orbit around the center of the Milky Way is what you're alluding to.
And right now, they're still feeling relatively strongly the effects of the sun over the galaxy.
Yeah, well, you can actually, if you go to JPL website, you can look up the Voyager missions. You can actually see a countdown clock, elapsed time since they left. You can see how fast they're going and all this, where they are in terms of their distance. And you can see they're slowing down because the Earth, the combination of the sun and all the planets are pulling on these spacecraft. Mm-hmm. So if there were no forces, they would go, of course, as Newton would say, at a constant speed in a straight line. Right. But there are forces acting on. It's the force of gravity.
Right. And so they're slowing down.
So they're slowing down.
Very minutely now, but they're still slowing down.
Yeah, they're still, just that they won't slow down all the way to zero and then reverse and then head back to the sun. They've reached escape velocity, so they'll never return to the sun.
Not without something else going on.
Yeah. Now, the other thing that happened recently, which is something that we had talked about also last day, was finally we have the launch of the Europa Clipper mission.
It's on its way.
So this happened actually yesterday. And it was delayed a few days because of the weather down at the Kennedy Space Center. So thankfully that cleared up and before the launch window closed, which is what you always worry about. Usually it's a mechanical issue unless you get really bad luck with the weather. That there's some mechanical problem that you have and it's going to take a few weeks to fix it. You want to be able to make that launch window, or you have to wait up to 2 years in this case later for it to occur. So thankfully, as far as I know, everything is going okay with the spacecraft, and so we just have to wait till it gets to Jupiter. Now you might wonder, what kind of path does it take? Well, here's kind of a drawing. It's not quite accurate because this was assuming the launch occurred on October the 10th, so it's only off by a few days.
Right.
So it went on 4 days off, right?
But that's
close
still
enough.
Significant. But
Yeah. So you can see the path that it's taken. It's not a direct path, and no spacecraft are these days. And, right. A direct path to the destination at hand, which is the Jovian system, Jupiter and its moons.
Until Starship comes online, we don't have currently a rocket powerful enough to go in a really direct flight.
Well, you could. You just have to make the payload
smaller.
Very little mass.
Yeah, so you could put enough fuel on it.
Yeah, well, the other idea is, imagine you could put one of these CubeSats on board. Send up enough fuel, there would be a direct way of doing it.
Right, okay, for a tiny mass, yeah.
But the thing is, you go through all that trouble and expense of launching it, don't you want a significant payload to do some multiple scientific investigations?
I do. I want some magnetometers and some neutron detectors and spectrometers and all that type of stuff.
It would almost be like sending a geologist to the moon without a hammer.
Yeah.
No, if you're going to send a geologist, you're going to at least
give him a rock hammer.
Give him a hammer so you can do some work while he's there.
Preferably with an auger and a drill, too.
Well, there, you added more weight to our mission. See, now we got to go the indirect way, Robert.
Okay.
Anyways, you can see from the trajectory that's given here on this slide that it is going to pass by Mars. So that's coming up in late February, if not early March now, of just next year. And then it's going to swing back towards the inner solar system again and bypass the Earth in December of 2026. And then finally, and each time it passes both Mars and the Earth, it'll receive a little bit of energy from the gravitational assist, the slingshot effect, as we call it.
And energy, you don't get it from nothing. Earth and Mars will lose a little bit of energy, but the effects are minuscule.
Yes. We're not going to worry about it, right?
Right.
If there's some activist out there that complains that we're stealing orbital energy from the Earth and these space launches, there's other things you should be looking at before you turn your attention
There's
to
other
that.
things you should worry about.
Right. But the arrival time finally is in 2030 in Jupiter.
Yep.
So
That's going to be a while.
So April of 2030. So write that down in your calendar, Robert.
I don't think I have a calendar that goes that far ahead, except for Google.
Hopefully we're still around by then, right?
Right.
Knock on wood.
Something. Knock on something.
Yeah, so this, I mean, and then the purpose of the mission, just to reiterate from before that we've talked about this spacecraft, is to explore the Galilean satellites of Jupiter, in particular Europa, hence its namesake.
Right.
And Europa is interesting. And Robert, you want to kind of summarize
that's
what's
a neat
going on
one.
with Europa?
Europa, we're as confident as we scientists can ever be that there's a liquid water ocean underneath an icy crust. So if you're wanting to talk about finding life elsewhere, Europa is a prime candidate because we even know it, kind of like Enceladus around Saturn. We know it's salty water even. So, holy cow. Yeah, we're going to send something there. We're going to try to investigate just how much water, what temperatures it's at, what's mixed in with it, and see if Europa's surface is actually active. In other words, do the ice act like crustal plates here on Earth and things like that?
And if you want to find out more details about it, you can refer to our past podcast that we did with Dr. Bonnie Beretti from NASA's JPL, who's one of the chief scientists on the Europa Clipper mission. And so there was a lot of things that we discussed during that podcast that is extremely interesting in terms of trying to seek out evidence potentially for the habitability of some type of life form, right?
Right.
So Europa is not going to determine whether there's life, the Europa Clipper, there's life on Europa.
But it can determine whether there's is it worth even trying to check, as well as just finding out about the environment. How much radiation is there from Jupiter's ionosphere and all that kind of good gravy.
Well, these places are going to be places that we're going to explore as human beings in the future, no doubt.
No doubt.
And so it makes, our solar system, distances within our solar system are extremely small compared to going to the nearest stars.
Right.
That's a real large leap in distance trying to get to the nearest star, Proxima Centauri, from here.
That's not, just getting to the inside the solar system is no small step. It's a big leap. And getting from there to the nearest stars even is hop in your car and drive for a couple of days. So.
Yeah, we have a lot to explore. Not only do we have the major planets, but all of their moons, the asteroids, comets. So there's lots of things to study in our solar system, including our own sun, of course.
Right. So
now the other major space news that happened in the last couple of days is that we had the 5th flight of the Starship. We mentioned Starship you did already today. And
it's a good vehicle.
Yeah, and it's very important because NASA is relying on Starship to eventually land on the moon itself as part of the Artemis project. And Blue Origin is the other company that's working on a descent vehicle to get to the surface of the moon. But, of course, Elon Musk with SpaceX is going to do more than that. His idea, of course, is to eventually go to Mars and beyond.
Right.
And so having a low-cost way of getting to space is very important. In fact, when I say those words, my mind immediately turns to the space shuttle, which was advertised as
That's what
the
it was
vehicle.
billed as being. Yeah.
Didn't work out that way too much. I don't know if it was sold to Congress on purpose, low-balled. Hey, we can fly this thing once a week, and therefore it'll only cost this much per pound, $100 per pound or something.
Right. Some ridiculous
and
number,
it turned out to be
honest.
many times greater than that. Many orders, several orders of magnitude more expensive, and never reached the reliability and the turnaround time that they thought initially. I don't know. Like I said, I don't know if the engineers. That's illegal if you did that, right? So
I don't think it was fraud or anything.
No, I
just
don't
think
want to say that.
They themselves overestimate what the capabilities would be.
Yeah, and then when we had accidents with it,
Right.
instead of having everything go on the space shuttle, all launches,
Right.
that was changed, and they tried to put as much as they could on unmanned launches after the Challenger.
Now,
for
on that
example.
second, the Challenger incident, I will sit here and go, I argued with some of my students that I was teaching at the time. They were complaining that NASA can't build anything that lasts. I was like, how many of you still driving a car that's 25 years old? And of course, none of them raised their hands. And I'm like, space shuttle is far more complicated than a car, and they've been running for 25 years. So, yeah, come on.
Yeah, well, don't forget, these spacecraft in general, they take, 10 years
To build.
to build, and so you're not going to just run it for a year. It
Right.
takes, the duty cycle on that is pretty poor. So you want to get at least double the time it took to make it out of it, like 20 years if you can go to 30.
Right.
Obviously, there are problems that happen, structural type of issues from
Right.
the engineering point of view that you always have to worry about.
And so the benefit of Starship is exactly like this picture saying, they are finding ways of making it cheap and rapid turnaround and reusability. And one of them was they caught it in the air.
Yeah, so that was the big thing. The chopsticks, as they call them, was designed to catch the first stage of the Starship rocket. And it has like 30 plus engines in the bottom, so that's not something you want to have crash in the ocean or smash on the land somewhere. Be nice if you can catch it, and then you can reuse some of that stuff.
Right.
So that's the idea, to make it cheap as possible.
Right. Now, to me, it does beg the question of how much extra fuel did you have to carry to get it to descend at a safe rate?
Yeah, well, so so you're going to carry fuel. I don't know
Right.
how many pounds of propellant you have to carry to do that. But the thing is, you still got more than enough,
Right.
leeway to get a sizable payload in orbit.
Right. And I wasn't trying to naysay the process. It clearly worked. But, you do have to ask these questions, because fuel is weight. So how much added weight did you have just to be able to recover it? But it apparently is still profitable to do it.
Well, given that there's 30 some odd engines in the bottom, you
Yeah.
would think that's
I
a lot of
I
money.
want to catch that.
Yeah, that's a lot of money. Just to make 30 some odd engines for these test flights is amazing. And you got to have a good assembly line process at work here.
Right.
And of course, the more you make, the cheaper they should be per engine.
Right.
So you get in the order of a few $1 million an engine. I don't know what the cost
I
is.
don't know either.
Maybe they don't tell people it's a private company, but I don't know.
Maybe we could have James back on the show sometime and query him about these things.
Yeah, it's just amazing what private companies can do versus what government operations manage to pull off.
All right.
So we've struggled how many years now to get the Space Launch System, the SLS, up and running. We've had a successful launch of it, of course, and now we're waiting for the second one to send humans to go around the moon and come back. But it's taking a long, long,
Right.
long time. And long time, we're talking billions and billions and billions and billions of dollars for all this. It seems like it's so inefficient in terms of time. Just think of this: for any of you who were around during the Apollo program, where did you think we would be in the year 2024?
Oh, I thought we'd be on Mars. I'm not going to lie. In middle school and elementary school, I thought we'd be talking about Mars and colonies on the moon and possibly science stations on Mars by now.
Yeah, the big thing was to be on Mars in the 1980s.
Right.
And I think von Braun's hope was to do that, land by the 1980s on Mars.
Yep.
And that, of course, didn't even come close to happening.
Well, you went from, a few percent of the national budget being thrown at it to less than 0.1%. So forgive me, but some of it is that we lost that as being a priority, and that plays havoc when you're trying to get something done.
Well, coming out of the 1970s wasn't great, the early 1970s, right?
Right.
So you're coming out of the Vietnam War, economic downturn. People are tightening their belts. There was the crisis with the oil, the Middle East crisis at the time in the mid-1970s. Then you run into the 1980s. Then you run into hot double-digit inflation. You think inflation's bad nowadays or has been bad the last few years. I mean, it was like, what, 20% in the
Something like
early
that.
1980s?
It was terrible.
Go get a mortgage for a house. I don't know what the mortgages were. What, 24% maybe? 30%? I don't know.
I don't remember.
I
was too young to remember.
I wonder what credit cards were. 50% interest on credit cards at that time? I mean, I don't know, right? I mean, it's just devastating. So that was a lot of years that added to all this stuff, right?
Right.
See, but a private company who can do things and make a profit, that's really where it's at.
That's where it's at. That's when things will take off.
Yeah. And that's when you can innovate even more, right? You're not
Right.
restricted so much, right? You're there, trial and error, try things, try to do it as fast as possible.
Well, I will say it takes off when you have more than one doing it. And right now we do have indeed two at least that are getting going.
Yeah.
On the smaller scale launching satellites, we've got about a dozen different ones.
Yeah, and it's
working.
not like this stuff is like making widgets, right? You're making
Right.
really advanced. It's rocket. They say rocket science, but really rocket engineering is what it is, and it's not for everybody, obviously.
Right.
So that makes a difference. But this flight on Sunday was extremely successful, as you can see there. And the first time they tried this, and it worked.
And it
So
worked.
it's amazing when you think about it.
Anytime you've got something that works on the first try, you did something.
Yeah, exactly.
So looking on the next thing.
So other stuff going on, in particular, this object, we're back to some observations with the James Webb Space Telescope that seems to show up almost in every podcast when we talk about astronomy.
I wonder why.
We're plugging NASA. NASA's getting their money worth PR-wise anyways, right?
Right.
At least from our podcast. Right? So this paper and result is interesting. It's looking at a star that's not that far away, not that far, quote unquote, 88 light years. And you're talking
Right.
about a galaxy that we live in that's 100,000 light years in diameter. So
Right.
88's in our backyard.
Right.
Okay.
Or
So
it's down the block.
yeah, it's not that far away. I mean, in fact, 88 light years, we talk about space exploration. Hey, in a few hundred years, we may get spacecraft, at least unmanned rope, who go around the galaxy and take over everything.
Right.
Von Neumann
Von
probe.
Neumann probes.
88 light years is not a big deal for them to do that, right? We can accelerate them up close to the speed of light.
And for those that are wondering, von Neumann probes are these machines that you send out. They find a planet. They take what resources they need to make duplicates of itself and send those duplicates out. So you've got an expanding envelope of these probes that are recreating themselves as you go along.
Sounds like something you'd get on your annual checkup or something, so you have to
Right.
be careful.
Yeah. Galaxy's going to be going to its doctor going, man, I'm infected with von Neumann probes.
You're not going to give me a von Neumann probe today, are you, doctor? No, that's next year. We'll save that one. That would be old enough. But anyway, so this star itself is in the constellation Lepus. And the interesting thing is there is planets going around the host star. So this is AF, Lepb. I guess you would call that B is the name of the planet.
Mm-hmm.
And the planet itself is one of the lowest, it is the lowest massed planet. And
That's been
how
directly
low?
imaged.
Yeah,
Yeah.
it's so it's 3 times the mass of our Jupiter, and that's been confirmed through direct observation use the astrometry technique.
Mm-hmm.
So if you want to, we mentioned that also last
Right.
time, but you want to say
So
what that is?
what astrometry is actually very accurately measuring the position of the star so you can determine how it's moving. So as the star is moving, if there's a planet around it, whether we can see it or not, whether we can transit it or not, whether we can spectroscopy pick it up or not, it'll make the star move as well because they're both pulling on each other. So this planet was determined to be there because of its effect on the movement of the star. If you want to think of it like this, you take your 3-year-old nephew or niece or whatever and tie them onto a string and you start swinging them around. They pull back. You still feel the pull.
Isn't that illegal in most countries now?
It
Robert?
is now, but used to we had fun with that. Being tied up and dragging each other around. So
Taking a piece of driftwood and slinging it around. the
yeah,
string.
yeah, that would work too.
You're safe
for
that
it.
way with that example.
Yeah,
But this particular Observation is important because the planet itself is getting close to the host star in its orbit, its normal orbit, as viewed from us, from the Earth. And it's getting closer and closer. In fact, right now, it's near the limit where the JWST can separate clearly the planet and the host star.
Right.
And so as time goes forward, it's not going to be too long from now before they'll get so close together they actually merge. And so you can't then be able to measure directly the properties of the planet,
Right.
because it's just too close to that star itself. So this was the time to do it, and they've calculated you have to wait roughly 10 years for it to keep moving in its orbit, so then they start moving away from each other as viewed from the Earth.
Now, we will not from any Earth-based telescope or even reasonable space-based telescope get the picture on the left.
Right.
The direct imaging pictures are those blue circles on the right. And basically to do it, you take the light of the star, model it, and subtract it out of the picture, and you're left with this little dot that's a little brighter than the surrounding areas, and that's the image of the planet.
In fact, the star itself, its light has been occulted, the disk, right? So the coronagraph that's used to make these observations, and the center of that star would be where the X is located in these figures on the right, the top one and the bottom one. And the planet is that bright dot that's sort of to the left of that X. So you can kind of see it. And the dates here, you can look at it carefully. So it's October 23, and the top one in January 24. That's not a big time difference, and you can see it's actually changed position as the planet orbits its star. And so you can get information about the orbital period of the star itself, and that's how we know it's getting closer to the host star, and eventually you won't be able to separate it for a while.
Yeah, in fact, it's confirming the orbital parameters that we'd gotten from the astrometry and the other methods of detecting the planet was there. They'd made determinations, hey, it's got an orbital period of this. That little dot's movement is on par with what we would expect.
And remember, these images that you're seeing there are direct images of the planet itself.
Right.
And that's not true for most of the exoplanets that we have observed. It's mostly done indirectly. So these are neat observations taken with the James Webb Space Telescope.
Absolutely. I like them.
Really cool.
So what's going on here?
Yeah, so the other thing I picked out in the news is it's kind of interesting. We talked a lot about galaxy formation and what the James Webb Space Telescope. Now, this is not data from the James Webb Space Telescope, just to kind of let you know, but there's been a lot of talk since James Webb has been up there making observation that somehow it's revamped cosmology and turned everything upside down and all this, a revolution in our thinking about where the universe came from and its origin and so on and so forth. And it turns out that if you actually look in detail at the observations themselves, they really say a lot about galaxy formation, not about the formation of the universe. Now, part of that is this observation, this paper, which was looking at a galaxy that's on the order of approximately 13 billion light years away. So it's not in our backyard.
No. That's, across the country.
And the observations then were looking at this galaxy using the ALMA array. Now, the ALMA array is an array that is at its multiple dishes that you could use to look at the same time at some source in the sky. And we combine the signal from the multiple dishes. And if you combine them properly, it's as if you had one single dish, and when it comes to resolution, that is the size of how far out these individual dishes are spread apart. And there's an image we'll show you in
a minute.
Yeah, that'll demonstrate that. But this object, then it's essentially a disk-like galaxy. So we think of our spiral galaxy, the Milky Way. It has a disk, and it rotates. So the sun, for example, it goes around the center of the Milky Way once every 240 million years. So we've gone around, 18 or 19 times since the sun formed.
Yeah.
Okay. And so this object is also rotating. Now, how do we know that it's rotating? Because we measure it using what we call the Doppler effect. So what you're seeing here is images taken from the ALMA array. So on the left side is the image of the galaxy itself. On the right side, it's been color-coded to represent the velocity shifts that we measure from the Doppler effect. And we have a slide that'll give you more information about that here in a second. But what you clearly can see on the panel on the right is that one half of that galaxy is bluish in color. That's the upper left, and the bottom right is reddish in color. So where it's red, that means that part of the galaxy is rotating away from us, and the part that's blue means that part of the galaxy is rotating towards us. So by using these type of measurements, you can get an overall view of how this object is rotating. So it's clearly rotating. In fact, it is the most massive, large-scale galaxy-sized disk that undergoes rotation that we've ever observed up to this point, being roughly 13 billion light years away. And remember, with that distance, that means you're looking back in time 13 billion years.
Right.
So you're seeing a galaxy that's newly formed, that's less than a billion years old.
I'm going to pause this right here to make a few points. Number one, the ALMA array is not a visible light telescope. It is our interferometer. It is a radio wave.
Yeah, millimeter, sub-millimeter wavelengths.
Right. Okay. Yeah, that's still radio. Yeah.
Yeah, it's radio.
So I was thinking it might be microwave, but no, that's still radio. So what's this reionization era?
Right. So the thing to think about is early on, the universe was extremely hot. Mm-hmm. So there is no way that you could have atoms form, because as soon as, let's say you think of the simplest atom, the hydrogen atom, as soon as a proton and electron bound together, there would be a very high energy photon around, and that would split them apart immediately. So if you have, photons with energy greater than a certain value, for those techno people, 13.6 electron volts, that has enough energy to ionize the hydrogen atom. Right. And so every time atoms try to form, they get split apart by the high energy photon bath that this material find themselves immersed in, which is spread throughout their whole early universe. But as the universe expands, the universe cools, and eventually the temperature drops below what we call 3000 Kelvin, and at that point the average energy of a photon is less than 13.6 electron volts. So then electrons can bound up with protons to form neutral atomic hydrogen.
Right.
And so as the universe continues to expand, it gets cooler and cooler, and you can form all of these elements that otherwise you couldn't form before, like hydrogen, like helium, for example. Right. But then eventually structure forms, like, for example, galaxies. And these galaxies then have newly formed stars. And we believe that the first generation newly formed stars are really massive compared to what we find forming on average around us locally today. And these massive stars are extremely hot on their surfaces, and they produce a lot of ultraviolet photons. And these ultraviolet photons, once again, can ionize matter. So you reionize the universe either through, and we're not exactly sure what's doing it, but we see the evidence that it's been reionized through the emission of very high energy photons from active galactic nuclei. People have suggested dwarf galaxies are doing it. These kind of things. We don't know exactly what is 100% the mechanism that's causing the universe to reionize, but it's certainly some of the things I've listed already. Right. In fact, that would make an interesting guest, somebody who actually works in this field, about trying to uncover what's responsible for the reionization of the universe. Right. So it has been reionized. And you can see that. How can you see that? Well, you look in the spectrum of objects at different distances from us, and you can see spectral lines that come from ionized various stages of different elements and molecules, right? So you know that it's happening, and they're immersed in this bath of photons. And if the photons are energetic enough, they will ionize the surrounding material.
Right. So, yeah, it's always been amazing to me and amusing to me in a way that star formation, because it reheats the gas that was cooling and collapsing in to form new stars. So the stars around it fire up and heat up everything and started expanding again.
Yeah, and we call that feedback.
Feedback, right.
So the old days, old beating, back in maybe in the 60s, people thought of these what we call closed box models, where if you're wanting to study like star formation, maybe you take a certain region inside like the Orion Nebula, which is a stellar nursery. So there's interstellar matter there that some of it is collapsing down to form stars, that you sort of draw an imaginary box around some site of star formation and ignore what's outside the box. And the goal was to make things as simple as possible. Because if you make it too complex, you'll never get anywhere. Okay? So you make it as simple as possible by having this closed box model. But what we realize is material funnels in and out of that box, in and out of those star-forming sites.
Right.
So to get a more closer match to reality, you want to have an open box. You want to open up the sides and allow for things moving in and out of that localized region of space.
But at that point, as mentioned, you up your complexity, and we needed modern computers before we could start really looking at that.
Now, do you recall I think, was it the last podcast where we showed that galaxy with that huge jet coming out of the center?
Yeah.
Well, that's an example of extreme feedback, because that jet is localized, and the fact that it's launched from near the center of the galaxy and it's pushing outwards, and it has an impact on any of the surrounding material that it's pushing on.
Right.
And it's heating it up, for example, instead of it collapsing, it needs to collapse, it needs to cool down, right? If you keep a gas heated, it'll never turn into stars, because it'll expand. When you heat the gas, you need to bleed off the energy to make it cold so it can actually collapse and allow gravity to do its thing. So we know those type of jets then, have a dramatic impact on what's happening around, internally in that particular galaxy. In fact, the unusual jet that we looked at was huge.
Huge.
So it has a dramatic effect on a huge length of space and large-scale structure of the universe.
I was about to say it'd have an effect as large as it is on nearby galaxies.
Yeah, it was like tens of sizes of the Milky Way in length, so millions of light years in length. So that would have a dramatic impact on a large region of space. So those are the type of things now. We know a closed box doesn't work for most things. You really, to get a most detailed understanding, you need to have that open box concept.
Right.
And with sophisticated computers that we have today, I mean, that's exactly what we're doing, is simulating, huge volumes of the universe as this open box type of concept.
Right. And then we go and we look through our telescopes and we see, oh, wait, no, that's not what's going on. Or we see, happily, sometimes, yep, that's what's happening.
And you know what you do then? If you find something that doesn't match the simulation, you tweak your simulation.
Tweak your simulation and you go
run
back
it over again and see what you get.
That's it. So,
And
getting back on the topic, though, I guess.
So here's the slide that shows you the actual ALMA array. So it's located in the Atacama Desert down in Chile at a really high altitude. In fact, so high that the average person, you probably couldn't walk around too much before you'd feel the lack of oxygen.
Right.
If you're from that area, the local people have adapted to those conditions. But you and I, Robert, we'd have an oxygen on our backpack.
If you're listening to me right now, I couldn't get up there at all.
And also, of course, for a snack, we'd have what? We'd have oxygen to breathe, but we have to take some food with us if we were there. Well, what do you think we should take for food?
Alpaca jerky?
I was thinking Milky Way bars.
Oh, of course.
Zing.
Of course. I missed that one. How about Mars bars? Do they even make those anymore? I just saw that.
They do. That's a Canadian chocolate bar. They make that a lot in Canada. But and if you look at my facial expression, we also bring Snickers.
Of course. Of course.
Now, the ALMA array combines signals from these independent dishes that you see here. And as I mentioned, the ultimate goal is to lower what we call the diffraction limit of the instrument.
Right.
So that allows us to see very high resolution. Now, when you're dealing with radio waves or even in the microwaves, you're talking about wavelengths that are really long compared to optical photons. You're talking about millimeters compared to in the optical, where violet is like 400 nanometers to red about 700 nanometers, where a nanometer is 1/1000th of a meter.
Right.
So the typical optical photon is a much, much shorter wavelength than you have at these type of wavelengths that ALMA is sensitive to. So that would give you a very poor resolution. And so to go get around that issue, you either have to build a very large single dish antenna, which can be very expensive and hard to do from an engineering point of view.
It starts trying to collapse under its own weight.
Or You build smaller dishes and string them together such that they're observing some object, and you can take the signal, combine it into what we call a correlator, and each of these dishes are hooked up to their own independent atomic clocks. So you can time the arrival of signals and correlate that together, and it acts like one single dish in terms of resolution.
Right.
So you can really, therefore, lower the diffraction limit of the telescope, providing that high resolution.
And I'm just going to warn people, doing that requires a lot of math. That's why we're not going into details about how you exactly do this. It's a lot of math.
Yeah, so you need a lot of computing power, which we have today, right? That's not a big issue nowadays, right?
Right.
So, and these arrays are the type of thing that are still affected a bit by the atmosphere, even though this is at a really high altitude in the Andes Mountains. And you want to get as high as possible because microwaves would be absorbed by water vapor.
Right.
And so you got to get above, as much of the water as you can. The best thing to do, of course, would be to put this in space.
Right.
Which ties the thing back into Starship, you see?
How often have we talked about
but I mean, it ties into that prior story, right?
Yeah. But how many times have we talked about the problems and how we wish we could get an interferometer in space? So,
well, if Starship gets cheap enough, that allows us to put up these without able to get enough money to pay for it, then that'll work good. But the Doppler effect is what you see illustrated here on the right. So do you want to go into that a little bit, Robert?
the Doppler effect is a nice tool for any time you're working with waves. So light is a wave. So what happens is as your source is moving towards you, it's emitting the wave, the next wave, a little closer than it should normally be. So that shortens the wavelength. That makes it shift, in the case of light, towards the blue end of the spectrum. Hence, we call it a blue shift. Whereas behind the object, in the opposite way, it's moved a little further away from the previous wave when it emits the next one, which stretches the wavelength out, makes it longer, which in the case of light means it's redder. And so we call that a redshift. So, yeah.
Yeah, so it's extremely powerful, allows you to get information about not only the relative motion of objects, but also to give you an estimate of how fast things are either approaching you or moving away.
Right.
In fact, the Doppler effect is, if you want to think of its impact on the history of astronomy, came to the forefront, if you like, very dramatically in the 1920s.
In the 20s?
The 1920s.
Okay. I mean, that would have been about the time of World War I, so...
Yeah, it was after the First World War.
Yeah.
And in the 1920s, the late 1920s, Edwin Hubble announced the fact that most galaxies, due to the observations of the redshift, most galaxies, if you interpret it as due to motion, are moving away from the Milky Way.
Right.
And theorists and others would jump on that, and they did at the time, to say that this shows us that the universe is in a state of expansion.
Which then Einstein's general relativity had said should be the case. Either it's expanding or it's contracting. It can't sit still.
Exactly. And now Hubble, it turns out, didn't actually want to take that intuitive leap to say that it's the universe that is expanding. He was cautious on the side of, okay, my observations are showing me that most of the galaxies have this redshift, and these galaxies are located in different directions. Now, if you want to come along and put your name on the line and say that it's due to an expanding universe, that's your business. But I'm just telling you what I'm seeing in my telescope. So he was, like I said, cautious of all of this.
Right.
And I think, as the story goes, it took him a while before he really accepted the fact that, it probably is the universe is expanding is the ultimate cause.
He was
of
like
this.
a lot of them at the time. He wanted it to be a steady state universe where everything was as it always had been and always would be.
Now, why would you want that, Robert?
It's comforting. The universe isn't really changing. It's been here forever. It'll be here forever.
Can you think of something also that you don't have to worry about if you think of a steady state universe, which we do worry about today?
The ultimate destination, if you will, where things are going to wind up, what's going to happen.
Now put the clock backwards.
Right. That means you've got the hot, dense, small universe. In other words, you've got a Big Bang.
Right. So you got to worry about the origin of the universe.
Right.
If you say that the universe, the way it is today, is the way it always been, it always has been like that for going back into the past as far as you want to go, and as we go into the future as far as we want to go, the universe will remain exactly the same, then the problem of the origin of the universe is now, if you could, in some ways, is gone, or you just push it in a different
you
way
move
of
the
thinking about
goalpost
it.
away. You know?
Yeah. But now we're in the situation that based on the fact that the universe has been shown to expand, that means there's a finite time in the past, 13.8 billion years as we estimate it today to be, where essentially there is no universe. That's the start of the universe.
Right.
So how do you get to that? How does the universe start? And what happened before that?
And we're still asking that question.
And we're still, in fact, some people suggest that time itself began at the beginning of the universe.
Right.
So Stephen Hawking was famous for saying that to say what happened before the Big Bang is like what's north of the North Pole. It's a meaningless question.
Right.
Others suggest that that's a cop-out. It just means that you don't have to think hard about it. Maybe there is a way of thinking, but maybe time did exist prior to the Big Bang. Maybe the Big Bang itself wasn't exactly the way we think that it happened, that something happened prior to the Big Bang, and we're just through this different cycles.
Right.
But then that's also pushing the goalposts, right?
Right.
Because then you say, what started the cycles?
Right. So
you're always going down. Who made the maker?
Right.
And that's ultimately what you're after.
And that's why I tend to agree with Stephen Hawking's interpretation that time started with the universe, because space-time is a thing, and asking what's before it's not pointless, but it's not really a before anymore. It's we've got to create a whole new language about it.
Well, you try to go at it from the point of view of physics, and one of the arguments that people make is centered around this whole concept of what we call entropy.
Mm-hmm.
Now, did you want to describe a little bit about entropy?
I will let you do that because I get all those ends mixed up.
Okay, so you can think of entropy as, and there's a couple different ways to think about it. A simple way to think about it, at least for this podcast, is you can think of it about the order of something. So if something is highly ordered, right? Mm-hmm. That means it has low entropy. And as stuff is disordered, so you take an egg that's highly ordered, it's contained within the shell, the egg mass itself. And then if you were to drop it on the floor and it splatters out, then that egg can go in different places. It's not constrained to be in that shell, in that volume. Now it can spread out over the kitchen floor, for example. So that's more states that it can be in. So that's a higher entropy. That's the way of thinking about it.
Okay.
So if you imagine a box full of gas and all the gas is in one corner of the box, the rest is a pure vacuum, then that would be a very low entropy condition because all the gas is in one location. It can't be spread out throughout the box into other multiple locations. So that's a very low entropy and situation or state. But if the gas is allowed to spread out and occupy the whole volume of that box, that means the gas is in different locations, essentially the volume of the box itself. So that's a very high entropy type of environment. Now, when you look at the universe, people have argued that the early universe is in a low entropy state, and as it expands and we go forward in time, it's in a higher entropy state. And if the universe has been cycling, there's no way to reset the entropy, at least people have argued this. Others have other views, so we won't go in there. There's always,
always somebody else that's got another idea.
And so it's hard to imagine, we'll put it that way, how the entropy of the universe can be reset. So then when you're coming out of the next cycle of a Big Bang, so Big Bang happens, expands outwards, then maybe it collapses in on itself, right? And then you have another new Big Bang and expands outwards to some maximum size. Then it collapses on itself, and the cycle goes over and over again. How do you reset the entropy so every time you're coming out of a Big Bang-like event that the entropy is low?
Right. Because from what we know now, it wouldn't. It's like a ball bouncing. It would still slowly wind down.
It's like a debt that you can't get rid of, and when you pass away, the family members that you have left have to accept that debt. And everybody in your family, every generation is constantly adding to the debt. There's no way to bring it back to zero. It just increases, gets larger and larger and larger, generation after generation. It's kind of like that. Now, is there a way to reset the entropy? Maybe.
Maybe.
People speculate. but we don't know for sure. I mean, people make a lot of detailed, nitty-gritty arguments about this, trying to figure that out.
I mean, we haven't seen anyway yet.
So this is one argument, and there are many other ones that you could use then to try to get something fundamental about the universe itself in terms of its origin and even its destiny, as you mentioned, is this whole entropy issue.
Right.
But, who knows?
Who knows?
Yeah,
Come help us find out.
That's what makes science, astronomy in particular, interesting. Is there's a lot of puzzles that we need to figure out. A lot of them.
A lot of them.
Yeah.
That's true of most science, though. There's a lot of puzzles.
Yeah. So if you're interested in science, if you're interested in anything at higher education, higher learning, I mean, please consider coming here to the University of North Dakota. We have a lot of fantastic programs that are not only on campus, but also online. So you can be anywhere, of course, and take online courses as long as you have an internet connection.
Right.
And with Starlink now, and probably more people have internet connections around the world than ever before.
Right.
So thinking about SpaceX, there's another connection.
There's another connection.
So you can come here or do things online and get involved in some of these programs, and maybe you'll find something that otherwise you never thought of taking and become very interested in. Who knows? Right. There's never a time when you can't start a new career.
Absolutely. Or just learn something new.
Yeah, just get involved. Anyways, so at the end of the podcast, we usually say a quote, and fittingly, the quote today is from
Edwin Hubble.
Edwin Hubble. You see how I worked that into the podcast?
I do now. I wonder about that sometimes. I'm going to start watching you.
So next time I'm just going to randomly select some scientist, grab a quote, and then try to work it into some storyline that we mention this person, so then it fits really well with the quote at the end of the podcast.
Works for me.
Now, then, just so before I forget, the next podcast, of course, will be next Tuesday. That's October the 22nd. And we are planning to have a special guest.
All right.
That'll be joining us. So for those of you
who've been around for a little while,
you'll recognize the person. And those of you who maybe are new viewing this podcast, I'll be seeing them for the first time. So that'll be in 1 week's time. And of course, if you like this podcast, don't forget to give us that proverbial thumbs up and subscribe if you haven't subscribed already. But the quote from Edwin Hubble, I'm delaying it because I'm waiting for Robert over there sweating. Here's the quote from Hubble. We find them smaller and fainter in constantly increasing numbers, and we know that we are reaching into space, farther and farther until, with the faintest nebulae that can be detected with the greatest telescopes, we arrive at the frontier of the known universe.
Woot. That is a good one.
Thank you very much for watching.
Thank you, folks.